Good morning, afternoon, or evening. My name is Johanna Teske, and in this pre-recorded talk, I'll be giving a brief overview of where we stand in the field of precision radial velocities and the useful and exciting synergies that I see that it has with TESS. This is definitely a very incomplete overview. I highly recommend checking out the 2020 Sagan Summer Workshop, which was all about extreme precision radial velocities, as well as the EPRV conference series. All right, to get started, if you're attending the TESS Science Conference, you may not yet be a fan of precision radial velocities, so why should you be? Here I'm showing two plots which are probably very familiar of planet radius versus orbital period and planet mass or minimum mass as we measure from the RV technique due to the inclination uncertainty versus orbital period. The pink squares are planets detected by the transit method, and the wine-colored circles are RV detected planets. And I have little Earth and Jupiter there. So you can see immediately in the right plot that the RV method has enabled the detection of planets at much longer periods due to the transit probability of a planet going as the radius of the star over the orbital distance between the star and the planet. So while clearly in both plots there are plenty of planets to study at shorter orbital periods, to get a full census of exoplanets, we also want to be able to know about and study those that are farther away from their stars and thus often cooler. I think a fundamental question driving exoplanet science broadly is how common are the types of planets that we have in our solar system, and precision RVs are already giving us a way to start to explore that question for the outer giant planets. The planet masses as measured through RVs are also kind of a key fundamental parameter of planets. The mass helps control the structure of a planet in what in its vicinity can be accreted, like during formation, and then obviously the interior composition via the temperatures and pressures at a given density. Deanna is going to talk more about planet interior compositions, but just to give you a preview, here I'm showing planet mass versus radius for detected exoplanets, along with these different colored composition curves, starting with pure iron in red at the bottom, adding more rock up to the green line, and then adding water instead of iron, and finally ending with a cool hydrogen helium composition curve up at dark purple at the top. So for most exoplanets, the mass and radius measurements combined will be our best clue as to their bulk composition. And I, in my own work, really find this plot to be fascinating, just looking at the variety of exoplanets that span this composition space. I also find this plot humbling in especially the mass error bars. So as we'll discuss next, we're working to make those smaller. Finally, focusing on the left plot, all these transiting planets, many of them detected by Kepler, that showed us that small planets, at least those close into their host stars, are common. And we didn't know this before because the precision of RV measurements just wasn't quite good enough. Despite the amazing contributions of Kepler and now TESS, the fact is that studying planets in detail, to do that, we really need them to be close by, or at least that makes it easier. And that means around a limited number of stars in the nearby solar neighborhood. In such that limited sample, we want to maximize our detection of planets and not just relying on those that pass through our line of sight. And so to find our full set of the nearest planetary neighbors, and probably truly to study planet habitability, which require detailed observations, we need precision RVs. All right, hopefully I've piqued your interest in PRVs if it wasn't there already. So where are we now in this field, and where are we going? In this field, big growth has come with advances in technology and instruments, along with analysis methods. So you can see here in this plot of planet discovery year versus RV signal amplitude in meters per second, that as the instrumental precision and analysis methods steadily improved over time, due to really tremendous effort by a lot of dedicated researchers, our sample of planet, the number of planets and the variety, the differences in semi-amplitudes that we could detect has increased. But for the last 10 years or so, we've kind of frustratingly reached a plateau of around 1 meter per second, maybe a little bit better. This is frustrating because to find those temperate terrestrial planets around the stars very close to the sun and try to characterize them to compare to the Earth, we have to do a lot better in terms of precision. A true Earth twin would induce a signal on the sun an order of magnitude smaller than kind of that current plateau in precision. And so on the left, on this slide, I'm showing a plot from Sam Halverson's Sagan summer workshop from 2020 that shows different planet RV signals as compared to the surface liquid water zone around stars of different temperatures. And as we'll discuss in a moment, new instruments are starting to push in the lower semi-amplitude, the right side of this plot direction. But it's entirely possible that we may never be able to detect planets with signals at that goal of 10 centimeters a second. On the right, I show a plot from Patrick and Peter illustrating what this signal might look like. This is a simulation, not real measurements. But you can see that in this simulation, these are observations over 10 years, thousands of measurements, with a precision we cannot yet achieve. So I definitely was like mind blown when seeing this plot. Why might we not get to that 10 centimeters a second signal detection capability? There are lots of hurdles in our path, including stars not being constant, well-behaved sources of light. The surfaces of sun-like stars are affected by numerous phenomena, from convective granulation to magnetic activity in the form of spots and plage and faculae. So this left plot shows these different physical effects. And then at the bottom, it shows actual time series of observations from the HARPS North precision RV spectrograph as it observed the sun as a star during the day. And those observations of the sun are in gray, and the Earth twin signal is in green. So you can see the sun just totally dominates. And this is shown kind of in a different way on the right plot, where we're looking at the time scale of different types of stellar variability and their effect on the RVs. And so these time evolving and sometimes periodic features have in the past been mistaken for planets and can severely complicate the interpretation of RV measurements, especially as we try to push down towards smaller amplitudes. I also wanted to say Belinda and Xavier will be giving more talks about the challenges of stellar variability in RVs on Thursday, so you should check that out. Another hurdle in our path is instrumental stability, or errors introduced by the instrument itself. For example, how accurately can my instrument monitor line profile? So this is some cool movies from the blog from the Habitable Planet Finder, looking at variation in the illumination of their fiber from the star moving across the spectrograph fiber face. So the right plot, the right movie is good. It's very stable. That's the system that they're using. There's also, stability of telescope and guiding, and things like even the detector homogeneity. So this is a plot from one of Xavier's papers looking at how lines in the HARP spectrum, so this is a different HARP South spectrograph, but as the star is blue or redshifted due to its motion of Earth around the sun, these lines cross block stitchings of the CCD and can influence the RVs, introducing systematic errors. Then there's just the time it takes to make small amplitude detections, especially at longer periods. So here are two examples of detections of small planets, Proximus NB, and at least a planet candidate around Barnard's star, although you should see this new paper by Lubin et al. But you can, in both of these cases, they needed really high cadence campaigns, observing the stars every night or multiple times a night for weeks on end. So really, how frequently do we need to make these observations to precisely trace out the planet's orbit and distinguish it from those different stellar effects? And can we find telescope facilities willing to dedicate that much time? And how does that fit into their scheduling? If we only want, 20 or 30 minutes a night, but over many nights, is that possible? Finally, what about the lines in my spectrum that aren't from the star of interest, but from the changing water absorption in Earth's atmosphere? RV errors added by these telluric features vary as a function of wavelength. And so in the optical, like this, the right plot from one of Sharon's papers, maybe you can model out the tellurics and get down to something like 50 centimeters a second. But in this left plot, it's showing that the effects of tellurics really increase as you go towards longer wavelengths. Maybe we can mitigate them, down to a certain level in the near infrared, but it could limit our detection capabilities there if our instrument is on Earth, which this whole report by Peter is about an RV spectrograph in space. So that's cool to check out. Anyway, each of these topics, each of these challenges is really a whole book in itself. And again, I encourage you to check out the Sagan Summer Workshop from last year, as well as the EPRV conference series, just as places to start to delve into the amazing literature on each of these topics. But of course, we're not letting those challenges stop us from trying to achieve that goal of 10 centimeters a second. And several relatively new PRV instruments are trying to push to an instrumental precision significantly below 1 meter a second, more like 0.5 or even 0.3 meters per second. So I just wanted to highlight a couple of these that have recently come online. First, we have NEWID, which is at the Wind Telescope in Arizona, the 3.5 meter Wind Telescope, and the PI here is Suvrath Mahadevan. And this is an optical instrument with coverage from about 4,000 to 9,000 angstroms, has a high resolution mode of about 90,000 or better. And while they have demonstrated this on-sky data of a precision of 50 centimeters a second or better, the error budget really predicts that they should be able to reach something like 30 centimeters a second. So it'll be really interesting to watch the progress of this instrument. It is public. You can get time publicly on it through Noir Lab. So that's an advantage too. And it's run as a queue. Then there's the Extreme Precision Spectrometer, or EXPRESS, at the 4.3 meter Lowell Discovery Telescope, also in Arizona. And this is built by Deborah Fisher's group at Yale. They are trying to achieve something like, I think, 30 centimeters a second. The resolving power with this spectrograph is more like 140,000. With a similar science bandpass as noted, it doesn't go quite as red. And this is some of their first on-sky data of this very famous 51 Peg planet. And then a measurement of this other kind of known giant planet with a big signal, but they're able to demonstrate residual RMS of 58 centimeters a second with typical single measurement errors of something like 25 centimeters a second. So that's coming along really nicely too. Then moving up in telescope size, there's the Shell spectrograph for rocky exoplanets and stable spectroscopic observations, or Espresso on the VLT. And the PI here is Francesco Pepe. This also is an optical spectrograph. Light from two fibers are recorded on a blue and red CCD mosaic. And the normal PRV operation mode for this spectrograph is also about 140,000 resolving power. They have on-sky data of Tau Ceti showing long-term precision of 0.5 meters per second or better, And then just in I think a single night, this was demonstrating something like more like 25 centimeters a second precision. And then this was just another example observing that Proximus NB planet. I just thought this was really impressive. This is now only using espresso data, and they're able to get an RMS of 0.27 meters per second for this planet. There are more talks about espresso also on Monday and Tuesday of the conference, so check those out for the latest results on new TESS planets, I assume. Then on Gemini North, 8.1 meter telescope, there's Maroon X, and the PI of this instrument is Jacob Bean. In these plots, a blue and a red arm, and the red arm is really designed to be optimized for observing M dwarfs. So the kind of 700 to 900 nanometer range is really where the optimal RV information content is for mid to late M dwarfs. And so that's what Maroon X is really focusing on, and they have these really nice results out earlier this year on GL486b, which was also detected by Carmenez and TESS. But I just was very impressed showing off the blue, but especially the red RV precision for Maroon X. So this is also a publicly available instrument through Noir Lab. So lots of different people can apply, which is cool. Oh, and Madison Brady will be giving a talk about Maroon X on Tuesday, so check that out. And then finally, moving even farther, like really into the near infrared, there's the Habitable Planet Finder at the 10 meter HET in Texas, also PI'd by Suvrath. And this is now covering kind of Z, Y, and J near infrared bands at a resolving power of about 55,000. Again, really optimized for M dwarfs, where they have the most light, and detecting habitable zone Earth-like planets in their around these M dwarfs. The planets are closer in, and also because the stars are less massive, the signal that the planet induces is larger, and so you don't quite need the same level of precision as in the optical, but this precision in the near infrared is incredibly impressive and really geared towards Earth-like planets around M dwarfs, and so that's what this detection is from a paper out by Suvrath earlier this year. There are lots of other spectrographs I didn't mention that are coming online now. Again, looking through the literature to get a more complete review is highly recommended. I also just wanted to highlight, kind of looking towards the future a little bit, there's the Keck Planet Finder, which is kind of in between this generation and the next generation, I would say, of PRV instruments. Obviously, this will be on Keck, and also an optical spectrograph, but covering out to close to 900 nanometers, similar to Maroon X, and really designed to follow up Kepler as well as TESS planets around fainter stars. So that's happening really soon next year. And then further down the road, we have all the giant ground-based telescopes that are coming online, and each of those has kind of a RV specific spectrograph. MODIS on the TMT is also actually the near infrared. HiRes on the ELT I think covers optical and to near infrared. And then GClef is optical for the GMT. And specifically HiRes and GClef are really trying to get down to 10 centimeters a second. That's really what their stated goal is. So we shall see if we can get there, and really what I'm excited to see is what we learn from this current generation of EPRV spectrographs that I was just talking about, and how we can apply those lessons to things in the next upcoming decades. All right, coming back to the theme of this conference, TESS, I wanted to finish with what I see as some of the exciting synergies and overlaps between TESS and precision RV instruments and science. In my own work, I focused on density measurements, but I'll leave that to Deanna to cover, and I'll go over a few other applications here. So first is using PRV observations to confirm single transit detections with TESS. This is an example from Dalba et al. 2020, where initially there was only this transit not in the gray parts of the TESS light curve, so only in sector 15. And so this team was following the star up with radial velocities, and they actually, got a constraint and were able to go back and look at the TESS light curve to find another transit hiding in sector 14 that was originally masked due to scattered light contamination. So that was a cool synergy between TESS, shining the flashlight, and the RVs really helping to confirm the planet. So this is Saturn-sized, sub-Saturn mass exoplanet in a roughly 19-day circular orbit around a bright F star. And so this planet has relatively low surface gravity and sort of low stellar insolation flux, so it's maybe a compelling target for transmission spectroscopy or measuring the Rossler-McLaughlin effect. Next, TESS observations can be used to help account for maybe those stellar variability signals that I talked about before. So this is an example of TOI 1v6, which actually was also, I think, originally a single transit detection, but then we got more TESS data. It was originally published by Deanna Dragomir as one of the first published TESS planets. And so this is a sub-Neptune that also has an inner, more terrestrial planet. But the period of the sub-Neptune planet, the orbital period, is very kind of dangerously close to the rotation period of the star. And so in this updated paper, we wanted to dig into that a little bit more and try to account for how the stellar activity might be influencing the RV measurements. And so Tianjin Gen published this really nice paper, also going into how much the stellar variability could influence the RV measurements, kind of running some simulations. So I suggest you check that out. And basically the message is, systems like this require extra attention to make sure that the RV errors and thus the mass errors aren't underestimated. We end up finding in this paper a density that is a little bit lower than what was originally proposed with the first observations, although consistent, I think, within 1 sigma. TESS observations can also be used to help actually choose RV targets. If you see, rotational modulation that you think is going to make it hard to make a mass measurement, that can be a way to select out targets for PRV observations. Also, part of the selling point of TESS was finding good targets for atmospheric observation, definitely with things like JDUS-T and HST, but also using ground-based high-resolution observations with PRV instruments, right, in the optical and near-infrared. Now, you'll note that on this slide, none of these are actually TESS-detected targets. I think that, is coming down the line. Right now, we're still finding TESS planets and confirming them, but I just wanted to show, I think what will happen in the future is characterizations like this for TESS planets. So we have these beautiful detections from HARPS North of all these multiple species in this ultra-hot Jupiter Kelt 9b. You can also look at the sodium lines, like these authors did for WAS 166b, and they actually found that the broadening was maybe indicative of atmospheric escape. And then there was this recent work on the ultra-hot Jupiter WAS 76, looking at the asymmetries in the iron 1 absorption from the atmosphere of this planet, and the authors concluded that this indicates iron is condensing on the night side of the planet. So these are all exciting for better characterizing the compositions of these planets, but also maybe getting into kind of atmospheric dynamics. I should point out that these atmospheric targets are really, that's a great result from TESS, but to really make the most and get the most robust conclusions from the atmospheric observations, we probably still in many cases need some constraints on the masses from PRV observation. So it really is kind of a symbiotic relationship. And so there might be more talk about that at the atmospheric characterization splinter session on Thursday. And then there's a talk on Tuesday about the TESS survey, building a statistical sample of sub-Neptunes primed for atmospheric characterization. So I'm excited to hear more about that. Finally, studying planets over a wide range of ages is kind of the next best thing to be able to study planet formation and evolution in real time. And so TESS is finding planets around stars that would just be really quite challenging to observe with just RVs alone because of their level of variability and in particular rotation. And so the K2 mission was starting to also find planets around young stars, and TESS has continued in that. So this was a detection of DS Tuck A-B from Elizabeth Newton, which is a 6 Earth radius planet in an 8-day orbital period around a 45 million year old star. And then with PFS, Ben and George, using slightly different data, measured the angle between the planet and stellar orbital axis, and showed that the planet is actually well aligned with the equator of the host star. Another very exciting young planet detection was around AU-MIC, which is a 22 million year old debris disk hosting star, about 10 parsecs away. This was led by Peter Plabchen, and TESS, you can see, made observations of this very variable star, but using several different RV observations, including iShell, which I didn't mention, but is another near-infrared spectrograph. They were able to detect and measure the mass of a transiting planet around this star in an orbital period of about 8.5 days. So this is really exciting, right? This is a star that has a debris disk from about 35 to 200 astronomical units, with clumps exhibiting non-Keplerian motion. And so finding a planet in this system is really like a jewel in the TESS crown, I would say. There have also been espresso observations trying to measure the orbital inclination of this planet relative to the stellar orbital axis, or rotation axis, and the planet also appears to be fairly well aligned, and so maybe we're starting to see a trend that these young planets are usually well aligned with their stars. There have been a couple of examples of that, although older planets are not always that way. We have plenty of examples of where they're not aligned, so I think we'll hear more about this from Christopher Worth's talk on Wednesday. All right, so just wrapping up, key takeaways from this talk are that precision RVs have been and will remain a critical tool for characterizing exoplanets, really complementary to transit observations in many ways in terms of the type of information, the type of planets that we can find. I talked about some hurdles remaining to reaching that goal of very, very good precision capabilities with PRV to enable us to detect Earth analogs. And I think distinguishing stellar from planetary signals is perhaps the biggest or most uncertain hurdle. But we're trying to rise to the challenge, and now is really a time of heightened development of new PRV instruments, and I didn't have time to get into it, but also analysis techniques, including using kind of sun as a star data that are really pushing our technical capabilities in both the optical and the near-infrared. And finally, there are these really powerful synergies between precision radial velocities and TESS that are enhancing the scientific impact of both, I would say, and opening up new avenues for understanding the compositions and formation of planets. So with that, I'll end, and I look forward to interacting with the other panelists during the conference.